Hello everyone. Welcome to the solution of LeetCode problem 99 named Recover Binary Search Tree. In this problem, we are given a root of a binary search tree where the values of exactly two nodes of this tree swapped by mistake. Now, we have to recover the tree without changing its structure. Suppose in the first example, if we see that the tree's root is 1, which has the left children 3, and 3 also has right children 2. So here the value 1 and 3 is swapped, and if we reorder the tree will become 3, 1 and 2, which is a valid binary search tree. And here in the second example, you can see that the value 3 and 2 is swapped, and if we swap the value 3 and 2, the tree will become 2, 1, 4, 3, which is a valid binary search tree. I hope you understood the problem statement. Now let's move on to the algorithm. Here, to understand the algorithm, we have taken this example. Now, this tree has root 16, which has two children, 5 and 15. 5 also have two children, 3 and 6, and 15 also has two children, which is 12 and 10. Now, what is the mistaken swap? Here, we have swapped the value 16 and 10 by mistake. That means if we place 10 into the root and 16 into the leaf and erase this 16 and 10, this tree will become perfectly binary search tree. Because if 10 is the root, then all of its left children value is smaller than the root. And if 16 is the leaf, then all of its right children value greater than 10. So here we can see that the value we have swapped mistakenly was 16 and 10. Now here, the first intuition behind the solution is if we perform the in-order traversal into a binary search tree, the result will be always stored in the sorted order. That means, suppose it has 10 and it has 16. Now, if we perform the in-order traversal, at first the call will be in this root, from this root to this 5, then the call will be this 3. So we will store here 3. Now the call will be in this 5. And from 5, the call will be this 6. And now the call will be here from 10. And from 10, it will go to 15. Sorry, not 15 here. It will, from 15, it will go to 12. And from 12, it will go to 15. And from 15, it will go to 16 as well. So here we have seen that all of the value is presented here in the sorted order if we perform the in-order traversal. So this is the first intuition. Now we have to check what if we perform the in-order traversal into the swapped tree. Now let's put 6 here. Okay, it's 16. So here, if we perform the in-order traversal, we will first be in this root. From this 16, we will go to this 5. From this 5, we will go to this 3. Now, from this 3, the call will be in this 5. And now in this 6. Now from this 6, the call will be into this node 16. Now similarly, it will be 12, 15, and 10. Because from 16 it will go to 15, then it will go to 12. From 12 it will go to 15. From 15 it will go to 10. Now we have two vectors or two lists of value. First one, the red one, is the in-order traversal pattern into the original tree, and the second one is the in-order traversal pattern into the sorted tree or into the swap tree. Now, what is the difference? The basic difference is the second list is not sorted because here from this pair 12 is less than 16 and from this 10 is less than 15. So both of the value 16 and 10 violates the sorted order. So here we can tell that in this tree, the value 16 and the value 10 violates the given binary search tree order. So if we swap the value 16 and 10, then the tree will become valid binary search tree. So this is the basic intuition. Now let's run a simulation. Here, at first, erase both of them. And let's erase the red one. Now, let's run a in-order traversal. At first, we are at this node 16. From 16, we'll go to the node 5. From 5, we will go to the node 3. So here, let's take our node, it is the previous, or we can say it is P. Now, from 3, we have visited 3, so we will get back to the 5. So for the node 5, the previous node is 3. And we have to check whether the root value, which is 5, it is greater than 3 or not. Yes, it is. So we don't have to do anything. The order is in the increasing way. Now from 5, it will go to the node 6. Now we have to make the value 5 as the previous node. So from 6, 6 is always greater than 5. So we don't have to do anything here. We will get back return. Now 6 will become the previous node. From 5, we will go to the value 16. So we have seen that the value 16 is greater than the value 6, which is the previous. So we don't have to do anything here because it is already in a increasing order. Now 16 will become previous because we have to store it into the vector here. Now from 16, the call will be in this node 15. It also has a left children. Now the call will be in this 12. Now there violates the condition. We can see that the value 12 is less than 16. But as value 12 lies in the right subtree, it should be greater than 16. So here we can see that 16 is the first missing element. Now we have found the first missing element 16. So we have to make the value 12 as the previous node because we are storing 12 into the vector. Now from 12, we will go to 15. We have to store it. And as 15 is greater than 12 or 15 is greater than the previous node, we don't have to do anything. Now 15 become the previous node. Now from 15, we have gone to the root 10. Now here again violates the condition. 10 should be greater than 15, but it is not. So 10 is the second missing element. So from 10, we will get back to the 15. From 15, we will get back to the 16. And from 16, we will return. And by simulating the in-order traversal, we have found these two missing value, and if we swap these two value, this tree will become perfectly binary search tree. I hope you understood the algorithm. Now let's move on to the code. In this problem, the code is pretty simple. At first, we are given a function named recover tree, which has a root as a parameter. Now, we are initializing the previous node with the minimum integer value. And now we are calling a inOrder function with this root. And inside the inOrder function, but before it, we have declared three of the variables: first missing node, second missing node, and previous node. Both of them are initialized with null. Now inside the inOrder function, if the root is null, we have to simply return. And in the inOrder function, now we have to recursively call the function on the left subtree. Now we have to process the root. That means if the first missing node is not initialized yet, and if our root value is smaller than the previous node value, then we have found the first missing node is the previous node value. Similarly, if we have found the first missing node value and root value is smaller than the previous node value, the second missing value or the second missing node will be the root. Now we have to initialize the previous node with the root and again recursively call the inOrder function into the right subtree. Now finally, we have to swap the value between the first missing node and the second missing node, and the tree will become valid binary search tree. I hope you understood the code. Thank you everyone for watching the video. We will get back soon with another LeetCode solution.